our software toolkit basically can take in any machine learning models or data sets and do this automated analysis. So we're going to walk you through a case study specifically designed for vector databases, and the particular data set is e-commerce. So this data set is from open source by Marqo. It's called Marqo GS 10 million. In their examples, they work a lot with this 100,000 sample subset. And this data set is constructed of queries to Google Shopping, as well as ground truth products. So, for example, a query in this data set might be television stands. Someone is looking for television stand products. We talked a bit earlier about how there's some ground truth information about what are reasonable outputs if someone looked that up. And the performance metrics, when you use case study data like this, are going to reward both the presence of correct answers and also the rank. So we talked a bit earlier how if you looked at a single query and you wanted to understand why the performance score was the value that it took, a performance score, for example, will be higher when it's rewarding correct predictions. So here, model B gets more correct predictions. So it's just a general notion. It had a higher score than model A, which incorrectly predicted an irrelevant product for this goal. So now an exciting example to lead into. Here's what happened when we applied navigable clustering to this case study data set. So in a matter of minutes, we surfaced groups of queries that the navigable clustering found. And also we were able to sort the table to find the ones with the weakest performing scores. So this is very related to the heat map concept that Gunnar was talking about. Now, what you're seeing here is providing novel information to the current frameworks people have access to today. Using the tools and approaches from today for vector databases and embedding models, you might get some average information across this entire data set of 100,000 queries. You might come across the information that the average performance score here was 0.34. So that's what happened. The performance metric in this example is NDCG. Now, when we ran the navigable clustering, we were able to easily get a table like this that showed us that pajama products had a really low score of 0.1, which is way below the average. And as espresso machine queries also performed way, way below average. And this is going to be really important for production scenarios where you do care about the performance, you do care about weak performing cases. So we're going to talk a bit about how to interpret these tables. The left column in the table called name, that is composed of keywords that are in the cluster of queries that we found. And furthermore, they are selected based on what makes that cluster of queries distinct from the neighbors around it. So Gunnar talked about theoretical foundations of TDA and how we have this structure about neighbors and data, and we take advantage of that information to give useful automated summaries of what is in each cluster. So rather than having to navigate like a complex visual, which is a common approach out there, and going point by point to try to form a theory of what is in a cluster, here we can give you an automated set of keywords that very quickly tells you, oh, like espresso queries are the ones that are performing really poorly. So this screenshot, what it actually is in Python is a pandas data frame, which is something that is kind of this universal tool for data scientists, universal Python package. And it behaves like a spreadsheet. So this is something that if you're comfortable with pandas data frames, you could play with it in Python there. You could also have this exported to Excel. And navigation of this table is very easy, just like Google Sheets or Excel. So you can quickly sort the table by the performance. You could filter it by a certain minimum size of the cluster if you want. You could search the name column as well. And because we made the navigation easy in a table rather than like an abstract visual, we were able to quickly get to this information that all these groups of queries perform way below average for the model. So we're going to pose a question. So what if you trusted a popular model out there from Hugging Face or Twitter and didn't do an evaluation of your data set? In this case, like if an e-commerce company used an E5 model, which is a reasonable popular choice of model to start out with, not until they deploy to production would there be like maybe they would start to get awareness over time that espresso machine queries are performing poorly. But with this evaluation approach, they could actually detect it ahead of time and take action instead of deploying a model that is clearly going to perform poorly on those kinds of queries. Other things that the navigable clustering gives you access to. So we talked about how the heat map helps you to focus on what's important to you in the data set. In this case here, we sorted for like what were genuinely the lowest scores, regardless of the size of the cluster. So here the clusters are smaller, but it's still important to know that look like kitchen spices and boys sweaters perform close to 0. And so if those were customers using an e-commerce site and the recommendations were close to like 0 relevancy, that could have a lot of consequences. And so a lot of teams, they're familiar with like the long tail distribution and how you do want to care about these like smaller case scenarios, because in aggregate, it could have a lot of consequences to your business if you don't support these users. We're going to talk about the next phase of the machine learning lifecycle and how this framework helps you. So we've shown you evaluating a single model, which was E5. Now we're going to show you how this table helps you to easily compare across models. So in our published case study on this e-commerce data set, the average performance of E5 was pretty good, like better than the expert model we also evaluated, like a comparison of 0.34 versus 0.26 for this metric. However, the navigable clustering surfaced a lot of groups that actually performed better in the expert model. And this opens some opportunities, like, do you want to do model routing? Do you care more about these groups that perform better in expert? Maybe they're more expensive or more popular products. Maybe they're products that are important to sell in season right now. By surfacing the groups of queries, you're able to take action, ask these questions about what's important to you in the data set. Another scenario we're going to pose to you that we've heard a lot about in the community is about saving storage costs and switching from a larger model to a smaller model. And we recognize that saving storage costs is very important, but it's also important to foresee what are the consequences of doing that. So this is a synthetic example, but the point it's driving across is as you change from one model to another, or you're considering doing so, you do want to find out not just the drop in average performance, but what kinds of queries could get much worse, because maybe that's a no-go for you if some important groups of queries are no longer supported. So here we see that cufflinks and cushions could do significantly worse. Next part of the machine learning lifecycle that people care a lot about is fine-tuning. So actually like improving their embedding model. So this is a real example from the case study where we used a popular e-commerce fine-tuning algorithm, and we took the E5 model from a 0.35 performance on the data set to 0.45. The maximum is 1, the minimum is 0. And we found many clusters of queries that got much worse from the fine-tuning process. So despite this average improvement from fine-tuning, these groups got worse. And that has consequences if you're going to deploy your model. But it's also an opportunity. So by becoming aware of what's happening, you can intervene. So it's possible that this fine-tuning run was a bit of bad luck. Maybe you need to change your hyperparameters. Maybe also that group of queries that is stagnating or getting worse has mislabeled data or needs more data examples to help the fine-tuning algorithm. So here, for example, we tracked a group that was hoodies based. So that's over there in the title. It says that hoodies and novelty hoodies was in a group of queries. And we're tracking several different performance metrics during the evaluation while fine-tuning from epoch 1 to epoch 14 ended up being the checkpoint that was best as we went to like epoch 25. And what we saw for this group, for example, is that there was just an absolute stagnation rather than an improvement happening. And what you saw before was that there are many groups that simply got worse. Next part of the life cycle is post-deployment. So we had identified in this case study, in this data set, for example, that espresso machine queries performed very poorly. And we surfaced that information, and that told us something novel that the average performance across the whole data set did not. Now, in production, models don't operate in isolation. They operate within your business model. And in your business model, you might be spending money promoting certain products through marketing. Now, if you knew in advance that customers would have a bad experience if they're searching espresso-related queries, then maybe it's time to prioritize other things in the meantime while you're trying to improve this experience here. Other choices you can make once you become aware about where the performance is and is not is that you can choose to support other systems to complement your embedding model system. So if you know this espresso machine experience is not going to work well in the embedding model right now, there are more like manual approaches you could set up to fix the output that you want your users to see. There's also cases where perhaps your vector database is supporting a chatbot. If you know in advance that certain kinds of queries are going to perform poorly because of this kind of evaluation, you could route the espresso queries to a human in the loop in the chatbot. We're going to go through some specifics about how this would work with the vector database as a ecosystem. So in terms of a workflow you might consider, you may start with some public leaderboards to get a sense of relevant models that are out there, and that could help you to narrow down ones that meet your size and speed and cost constraints. You could start with an evaluation of average performance to give you a sense of, some of the better models from some of the worst. However, the step 3 is really important, which is the navigable clustering we've shown you today, which helps you to understand the actual pros and cons on your data set of any model. And once you become aware of those pros and cons, you could then choose the best model for you, fine tune with more precision, and also use your models with more precision. In terms of actual data to do this kind of analysis, we use like standard evaluation data that people are using, can pass in easily to the Python framework, for example, structured as a pandas data frame. If that information isn't calculated yet, there's a couple of frameworks that we've put out notebooks to help people with. So for example, Bear and PyTrek eval help people to evaluate models on their data. And if for example, ground truth data and doing evaluation is not something that's accessible in the near future, you can still do TDA clustering to get groups on your data. So some metrics that are popular, and this framework supports really any metric that you've saved information about. And some ones we come across for vector databases, precision and recall. There's also ones related to the quality of ranked outputs like NDCG. You can also pass in live user behavior data as an indicator of performance. So click-through rate and purchase rate tells you a lot about your queries. To show you a visual example, at the screenshot below is a pandas data frame. It looks like a spreadsheet. What we're showing you is each row contains a query to your vector database for which the evaluations has rewarded it with a certain score. For example, these scores are between 0 and 1, and we're showing you like 5 different metrics just as an example here. In standard evaluations, you need at least 1 score per query. You could have multiple. Here's like an input output example. At the top is what we're talking about, which is you come into navigable clustering with at least one score per query. For example, here we show NDCG as the score. Row one could be kitchen scissors and the score could be 0.44. And the output that navigable clustering can help you get pretty quickly, and honestly a matter of minutes, is different rows containing the clusters of queries. And that tells you how many queries are in that cluster, what is the interpretable keywords for it, and we summarize for you an average over that cluster to tell you what's inside. Another example here, if you pass in this information for multiple models, we can help you build a table. For example, in the table below, we compared SBERT to E5, and we quickly summarized what the best model was and by how much. So because we were able to use a table, we're able to easily construct this model comparison on your data set. And if you're watching the recording later, feel free to pause the video and look at it deeper to get a sense of it. If you don't have evaluation scores, so we're talking about how clustering can still illuminate what kinds of queries are in your data set, that helps you understand what to prepare for and what could happen. Here, for example, from the case study, lots of groups of queries, wigs, visors, how many there were. Also, if you don't have evaluation scores for your own data set, there are evaluation scores on public data sets. So if you're choosing an embedding model that's been publicly evaluated, those public evaluations and the data used for them could be passed into navigable clustering. And that could help you to foresee some important scenarios. So for example, if you were building a legal chatbot and you don't have that kind of evaluation information for your own data set, it's very likely there's lots of good models out there that have been evaluated. You could do navigable clustering on those, and perhaps you'll surface that the model that's good on a public data set is not good at DUI cases. And so if somebody asks your legal chatbot about DUI, perhaps you should route that to a human expert instead. So some concluding thoughts, perhaps a visual to hold on to, is that looking only at the average performance on a data set doesn't illuminate the actual groups of queries that are not doing well. For example, in our case study, the average performance was 0.34, while here we see many groups of queries that performed far worse. For example, espresso machine queries, here we see 30 and performance is 0.11. And navigable clustering brought to your attention, here are the critical and actionable performance problems in your data set. And a high-level summary, so why navigable TDA clustering? It gives you this performance breakdown on any embedding model on your own data set. Because we have a table, it makes it easy to compare models on those clusters. And then with precision, this helps you to improve your models and deploy them with more exactness. Some resources. So we have checked in yesterday, looks like over 1,000 people have been trying this out. We're on GitHub and we've got a Slack community, and feel free to reach out to us with questions and engage with us on examples and whatever you're curious about.